Let us start today's discussion. We'll talk about discrete Fourier transform today. And before we start discrete Fourier transform, let us look at some applications of Fourier transforms, which we said that we will do in the end of the last class, but we could not. So some applications, examples of applications. All right. So this is not by any means an exhaustive list. This is just something that comes into mind when you do physics or physics with Fourier transform. And all these applications I have chosen such that they also have some computational value, such that you use this application with the Fourier transform in a computer. Now, how do you do Fourier transform in a computer is what we will learn basically today. But before that, let's see that where we will use them. So one thing that should be already clear to you from our discussion in the first day, so how you introduced to Fourier transform, that you wanted to know the frequency content of a signal by using the Fourier transform of the time series recorded, the signal recorded as a function of time. So what do you mean by knowing the frequency content of a signal? So it has a name which all of us know. It's the spectroscopy. And here you are using a Fourier transform spectroscopy essentially. So that should be plain and in your understanding. The other thing which is quite related. So when you say Fourier transform spectroscopy by means, when I say frequency content of the signal, I mean that the frequency in the usual sense of frequencies. The time domain signal is then changed to the frequency domain. But then there is other type of frequencies which we talked about last time also, which are like the spatial frequencies or the wave numbers. So wave numbers are sometimes called spatial frequencies also. So you use Fourier transforms to know about the spatial frequency contents of the signal. So this is essentially, we are going to the realm of optics, and we are talking essentially about the Fourier. There is a way of looking at the diffraction using the Fourier transforms. So this is this is essentially the theory of diffraction. Sometimes they are called Fourier optics as well. Okay. And then there is other place where Fourier transform is used extensively is image processing, which is related to what I have written in optics, but this itself is a huge area and huge industry. So let me write that separately. It's used in all sorts of places, including the image processing which is happening in your mobile phone when you take a photograph. But in context of physics, the first place that comes into mind is astronomy. So in astronomical image processing, in astronomy actually, whatever you have written so far, whatever I have written so far, all of these are used. There are telescopes which works in the radio wavelengths mostly, uses the Fourier optics to make an image. There are telescopes which uses the Fourier transform spectroscopy to know the frequency content of the signal. And then you do image processing in astronomy using a lot of use of Fourier transform. And then, which is now completely coming to a rather theoretical domain, is to solve the linear partial differential equation. One uses Fourier transform. And I will request the MSc students to give me an example because they have already studied this. Where do you use Fourier transform while solving linear partial differential equations? And
Solving heat equation.
Heat equation.
Schrodinger equation, fluid equation. What is the technique called? There is a very distinct technique which you have studied, which was in your syllabus. of one of the courses in your first semester, and I did not teach that course, right? So to solve for the Green's function, remember that you used the Fourier transform. Actually, in many of the applications uh, where I will use a term which, if you are not familiar with, is all right, where you have a mean field theory, where you can describe the distribution of the position of the particles in terms of a density. You use to solve the differential equations in the, if they are linear, in the Fourier domain, and then you, once you get the solution in the Fourier domain, you back Fourier transform it to the real domain. So that's a very useful and widely used technique. And so, like, for example, one example that comes into mind is the case of evolving the universe itself. So in cosmology, people like to see what happens to the universe if you put in all the initial conditions correctly and all the physics that you know, how the universe comes about as it is today from a very early universe. So there, because the computation is very large, so one has to use this technique of solving the linear partial differential equations, in that case Poisson equation mostly, using Fourier transform techniques. And without without the Fourier transform techniques, it would not have been possible to know about how the universe evolved. All right. So these are the some of the uses, and some of these uses also will come into our discussion when we'll in the next class, and then in the lab when we will do Fourier transform. So any questions so far? All right. So let us switch topics, and let me go to the next page because it will be completely different topic now. So okay, so let me come back to the previous page and remind you of how we defined the Fourier transform and the back Fourier transform. So because that will be helpful for us to go ahead in time now. So we have, I am working in the time and frequency domain today because it's easier to understand there. But all that we'll talk about will also appear, or is also applicable in any other domain and any dimension higher than one. So we'll restrict ourselves to, so 1D and the time frequency pair. So T and nu, if you wish. This is just the sake of understanding purposes. It can be generalized to anything that you wish. So this is given by integral of -infinity to +infinity. This is what we wrote last time. I will change the notation a little bit just for the convenience. E to the minus I 2 pi nu t d nu, and then we wrote epsilon nu as and remember that when I have 2 pi in the exponent, then I don't need a normalization factor. Okay. So just to make sure that this happens for any signal, so we'll change this a little bit. So these were our Fourier transform and inverse Fourier transform relation. Let's say that we all understand this. So these are AT, and so this is an important thing, that these are continuous functions. Okay, so when I say continuous function, in general they are continuous function. Obviously, if I have anything which is not continuous, it will still work. So let us go ahead and let me introduce you with the discrete Fourier transform. Now this again you may have already studied, but you may have only looked at the final formula, and it is important that we go through how the final the expression for the discrete Fourier transform comes about, and understand that where are the approximations going in, and what are those approximations, and what are the extra properties in the Fourier transform that we introduce during those approximations. Okay, so why do we need a discrete Fourier transform? Because if I have a function, so if I have a function fx, it's an analytical function. So it's known at arbitrary precision with x and for all x. So that's, if you don't know that, so then the function is not defined, right? So let me ask you that what is the problem in implementing such a function in a computer?
Sir, the precision is unknown. So and
So finite precision is the problem. What is the
yes, sir.
is there any other problem?
So we can't actually store all possible value of fx in the computer because we need some access to form a picture at least.
So I have also finite extend. So I cannot store x up to infinity, right? So I have these two problems. So one has to realize that I can store this at a finite precision, say delta x, and I can only store up to a certain x max. You cannot store for all x. Okay. Now I write x max by assuming, so let's say we store or we evaluate the function with delta x as our precision, and I evaluate from 0 to x max. Now, can I always only evaluate from 0 to x max?
We can do it from any point x0 to x0 plus x max.
So we can do it from any point from x0 to x0 plus x max. So I can do it instead from x0 to x0 plus x max. And last time we discussed a theorem called the shift theorem, which so if I can calculate the Fourier transform between 0 to x max, I can use the shift theorem to know the Fourier transform between x0 to x0 plus x max, right? So and then so I can, so this can be folded to this using the shift theorem. Okay, so then there comes the importance of the shift theorem, that you can fold the function back to 0 to x max if you know it in between x0 to x0 plus x max. So what this will gives rise to is a finite number of samples in the function. So finite sampling. So what do I mean by sampling? I mean that the x is not known at all points. It's only known at the points at an interval of x max by some n, and that is what is delta x. Okay, or to say it more precisely, so we consider n regular samples, regular and continuous samples. Sorry, I do continuous sampling means that I do not sample the function at some points and then give gap and then sample it some other points. I also do regular sampling, which means that if I talk about a particular TL where it is sampled, so that TL will be given by L times delta T, and L belongs to 0 to, so I have n samples, so if I include 0, so this is n minus 1. So what I am sampling is that at delta T 0, then delta T, then 2 delta T, up to n minus 1 into delta T. So your T max is n minus 1 into delta T. So this you realize that this is n minus 1. That is just to include 0. And also, let us talk about a few things here which will not make much sense for the time being. At the end of today's lecture, or if we can spill over it to the tomorrow's the next lecture, we'll probably make it clear why we are making these assumptions. For the time being, we are just assuming that n is even, so it can be done for odd as well, but just to put some points home, so we say that n is even, and the function a as a function of t has finite support. Can anybody elaborate on what is finite support? What do you mean by finite support? So it means that a at t is not equals to 0 only in a range in t. Okay, because then, so it's like, for example, if I take a box function which is non-zero between 0 to 1, so that that is a example of such a function. Okay, so why you want to take that type of function only, at least for this discussion? I am not saying that it cannot be done with other functions, but why we want to take such examples only? It is because we are evaluating the or sampling the function between 0 to t max. What exactly sampling means we will come about, we will talk about later, but we are just evaluating the function between 0 to t max only, and we are assuming for the time being that the function is non-zero between 0 to t max. Everywhere else it is supposed to be 0, so there is no contribution from anywhere else, and that is, it is clear why I want that. I want that because when I do this integration to calculate nu, then this integration goes from minus infinity to plus infinity. So if my a as a function of t has a value between minus infinity to plus infinity everywhere, I cannot just do this integration knowing its value at a finite region in t. So I'm assuming that I know only in a finite region, and then doing it. All right, any question?
So,
Yeah.
so like where we have written finite sampling, why did we divide by n minus 1 instead of n?
Because we start with 0, right? So L can go from 0 to n minus 1. So if I ask the question, what are the values of TL? TL starts from 0. So what is the maximum value of this? TL is one of the values of T where you are sampling, right? So you are sampling at T at 0, T at 1, T at 2, T at 3. T at 0 is 0 because L is 0. T at 1 is delta T, etc. So you can go up to only T n L minus, T n minus 1, which is n minus 1 into delta T. So that is your T max, right? Is that fine?
So what's the problem with taking t max as n delta t?
You can take, so then you have n plus 1 sampling. Just
Okay.
because we want an even number for the time being, and in plus 1 can also be even, but we have kept it like that. So you can define n plus 1 samples and go through the entire things. That is all right. Okay. So the input is constant, clear, right? So we are trying to discretize a Fourier transform relation, which is, so let's say the continuous relation I will write here, which is a as a function of omega or frequency. We are writing in terms of f, which is minus infinity to plus infinity. So this is the actual Fourier transform relation. And we have already seen that what is my a. So a at t, which was a continuous thing, now is sampled at t equals to TL. So I can call that AL. Okay. So these are discrete values of the function. How many of them? N discrete values of this function. So this is what goes as my input. So this I can call this as my input, because this is what goes in here. Okay, so let's ask the question, what can we get at the output? So what can we get as small a as a function of nu? Okay, so this is a question we are asking. Now, if you look at the Fourier transform relation carefully, you will see what you are doing with the inputs are a, t, is that you are multiplying each of the input at each different t with some complex number, which is the exponential part, and then adding them up, right? Integration is the limit of a summation. I forgot the dt over here. But the integration is the limit of a summation, so you are essentially adding them up. So you are multiplying the inputs by a number and then adding them up. So that's a linear operation, right? So Fourier transform is nothing but a linear operation of this AT. So it's kind of average of the input values of AT. Is this point clear? That Fourier transform is a kind of average of the function AT. It's not this plain average, but it's a kind of average. Right?
Yes, sir.
Now, you see, because it's a linear operation, if I have n inputs, there is no way I can get more than n outputs which are independent to each other. So n independent inputs can only give you n independent outputs, right? Because you are doing linear operations. So if you want to get n plus 1 outputs, they will not remain independent. Okay, this should be clear from your linear algebra whenever you have done. So this is a very important point. So n independent input will give me only n independent outputs. Independent is important. So which means I have a l n values. So I can estimate a nu at n nus independently. Okay, and again, so because now I again only can estimate it at some n values, which means that now my n, the frequency domain has to be discrete again. So this also has to be discrete. And a nu max. This is again because this we have gone through once, so I will not. I mean, we don't need to go explain again that why there should be a delta nu and nu max, but there has to be a delta nu and nu max because I have a finite number of sampling in the frequency domain as well. Okay. So let's say that we'll estimate it. So a nu will be estimated at n different, let me write, n independent rather values of nu with precision and I choose these to be from minus nu max to plus nu max. Okay, why I choose from minus nu max to plus nu max? Because my integration here by definition goes from minus infinity to plus infinity. So I cannot infinitely obviously integrate from minus infinity to plus infinity, but I choose from minus nu max to plus nu max. And then I choose nu max to be, so this, why I choose this like this will be clear later, but let us say that I will choose this to be that 1 by 2 delta t. Okay, why it is 1 by 2 delta t, it will discuss at the end of, probably we'll discuss it in the next class. Okay, so if this is so, and I am choosing minus nu max to nu max, and there are supposed to be again n samples, so I can write kn. So kn is the discrete values of k, just like we wrote xl. So now I have discrete values of k. So this is n into delta k. And if you calculate, so now I can calculate delta k. So delta k is 2 nu max divided by n. So delta k will be, so this I can write as n by capital N into delta t. Because I have 2 nu max here, so from minus nu max to plus nu max, the total range in nu is 2 nu max. That 2 cancels with the 2 over here, so I will get small n by capital N delta t. Okay. Now what is the range of n? So n has to belongs to now minus n by 2 to plus n by 2. Because when n equals to minus n by 2, so then you will get nu max. You can put it over here. So if I put n equals to minus n by 2, so n capital N cancels out, I get minus 1 by 2 delta t, which is minus nu max. Okay. So do you see any problem at this point? Please look at it. I will give you 1 minute to go through this, and then if you see any problem at this point, tell me. There is a problem at this point, which we should. How many values of small n are there? How many values are there where small n is negative? Small n is the integer, right? So it goes 0, 1, 2, 3. And remember that capital N is, we have chosen to be even for this discussion. So if capital N equals to say 6, how many values of small n are there?
7.
7.
7. It goes to 7. Okay, right. All right. So if it's 6, there are 7 values of small n. Now that is problematic because we said that there can be only n independent values, right? So this you will see that minus n by 2 and plus n by 2 are dependent. In fact, the function evaluated at small n equals to minus n by 2 and plus n by 2 will be the same, will have the same value. They are equals to each other. Okay. So this we will see shortly. So because minus n by 2 and plus n by 2 is dependent and only those values are dependent, then you say that you have n independent values only. Okay. You include one extra for convenience because then you can write it symmetrically between minus nu max to plus nu max. Okay. Sorry, I'm mixing up the spatial frequencies and the normal frequencies sometimes, because when I use these formulas, I use mostly spatial frequency, but it is easier to understand with normal frequencies. But anyway, so is that fine now?
So where you have written minus Vmax to Vmax, what does that mean?
See, like just like when you talked about the x domain, the t domain, sorry. So we have the function defined in the range 0 to t max, right? So I can only define it at a range with a finite precision. Similarly, for the frequency domain, I am defining it with a range which is minus nu max to plus nu max with a finite precision, delta nu. Okay. Is that fine?
Yes, sir.
Okay. See, I am doing it, this function here, a as a function of t, it can be defined at any from one t to the other t. But when I want to do the integration is always from some minus number to the plus number, right? Minus infinity to plus infinity. Because I have to cater to the integration, so I just define it like minus nu max to plus nu max.
Sir,
Yeah.
sir, how did that small n delta nu become equal to small n upon capital N delta t?
Because I have nu max as this, and what should be the delta nu? Delta nu should be 2 into nu max by n, right?
Okay, okay. Okay, okay.
So that you put in over here. I missed a step. All right. So let's go ahead and see what happens with all these things. So let's see what we have done. So I have a as a function of nu. Write the continuous expression here. This is n and t into capital N. N belongs from minus n by 2 to plus n by 2. And the function the function a as a function of nu, this we will evaluate at nu n. Okay. So with all these, what can I write? How can I write this expression? So I can write this expression a nu n. I have to approximate it. I am writing the approximation because the integration is not from minus infinity to plus infinity anymore. It's from minus 0 to plus t max. And you assume that the function is within that. So the integration becomes L equals 0 to n minus 1. That is the range over here. AL, and what do I have here? I 2 pi. Nu is supposed to be replaced by nu n, so that's the discretization of that. So this is n by delta t capital N, and t is supposed to be replaced by L delta t. And then you have the measure of the integration, which is delta t. So we define this now an just like capital AL, which are the samples of the function in the t domain. So these are the samples of the function in the frequency domain. I define these as nu n by delta t. So this is equals to L equals 0 to n minus 1 AL e to the I 2 pi n L by capital N. See, small n L by capital N, all these three are numbers, just numbers. Okay. So this is the discrete Fourier transform relation. Note that an is kind of the density of the function in the sense that you divide it by delta t. So you have to remember that when I define an, it is not just like here, which is capital A as a at TL. It is small a at the frequency nu n divided by delta t. Okay, and then you also realize that there is a chance of truncation error here. So this we will discuss in detail in the next class, what it gives rise to, what it may give rise to. But there is a chance of truncation error here because you are not integrating the function from minus infinity to plus infinity. You are the summation is truncated at a finite number of terms. Any question? So I have not written the inverse relation yet. So let us go forward, and I will carry this definition of DFT in the next page. You realize that so I have no reference to x and k here in this entire expression. There is no reference to x, or sorry, t and nu anywhere in this entire expression. So that is kind of remarkable, because usually when you write down, so you have a delta t or delta t or delta nu, so those things are gone because of just the definition of this. The next thing we realize is that this function an, or this, if you call it a function, these values of an, they are kind of periodic. So let's calculate what is an plus capital N. So what is this? So an plus capital N, so for this is for a value of L, so particular value of L is summed over, so for all values of L. So an plus capital N is that I have to sum over L, obviously. The small n part, so this here I should write small n plus capital N by L, sorry, times L by N. And that you will say that is L equals to 0, N minus 1 AL, A to the I 2 pi small l N L by capital N multiplied by e to the I 2 pi L. Right? So you realize that now if I go to for each L, so if I go to each L, then this thing is the value corresponding to that L, and then this is just a complete period, right? So L goes from 0, 1, 2, 3, etc. So I can write this as same as an, because see, e to the power I 2 pi L is same as e to the power I 2 pi into 0, because L is the period of the function. So cos of 2 pi x is same as cos of x. Sine of 2 pi x is same as sine of x, if x is integer. Is this fine? So this function has a period of n, or an has a period of n. Any question here? So because it has a period of n, I can do a shift in the function, right? So period of n means now what apparently looks like infinite x-axis. So what has happened is I had an infinite or k-axis, new axis. So in this both ways it can go up to plus or minus infinity. But now first thing you have done is that you have truncated it to minus nu max to plus nu max. But then you also realize that it has a period of 2 n's, and remember that nu max and minus nu max is, it has a period of n. Nu max corresponds to minus n by 2, and these are like this. So it means that minus nu max, or the value at minus nu n by 2, is same as the value at n by 2, which is what we said earlier, that those two values are not independent. So this I can as well think, because it has a period like this, so you can as well add these 2 points together. So that is nu max or minus nu max, the same point, and this is 0. So this is positive nu here and negative nu here. So they fold back to the same point. What all I am doing is that if I have a ribbon like this, which is circular, cut the ribbon here and take this ribbon right hand side and this in the left hand side in the horizontal axis, that will give me this number, this axis. So we can, instead of, remember that at this point this is my plus n by 2, which is also my minus n by 2, but I can shift it such that I can shift it a little differently. So I can say that I will write for a n minus 1 or a minus n, I will shift it to a of n minus 1. Sorry, n minus n. Okay. So then what will happen is, then instead of going from minus n by 2 to plus n by 2, things will go from 0 to n again. 0 to n minus 1 rather. Okay. So if I do that, then remember this n was going from minus n by 2 to plus n by 2, but now I have shifted my n's, or shifted my values in the frequencies, because it's a periodic. So periodic means I call it 0 here or 0 here, doesn't matter. So I've just rotated my 0 somewhere else. And by doing that, I have folded my frequencies from 0 to n minus 1. So I can write the inverse transform as unfortunately, if you do it properly, you will see that there is a 1 by n coming over here. And just like we said for the case of Fourier transform, here also we do the normalization symmetrically and put that n divided into 1 by root n in the 2. So this is inverse DFT. So I'll stop here because it's already out of time, but we will start from this slide in the next discussion.